So we started this the other day, this idea of sequential logic. So today we're going to talk about flip-flops, which are a type of sequential logic. It has two states, set, reset, and kind of goes back and forth, and has a type of memory. It doesn't really have memory like RAM or anything like that, but based on previous states, it possibly could remember what happened. Okay, so the easiest form of this is called an SR flip-flop. SR stands for set, reset. And it's really just two NOR gates. But remember how last time we talked about the way the couple with feedback, one is feeding back to the other. Okay, so that's actually really makes it kind of the magic that it has. So it can also be made with two NAND gates. We're going to see an example of that too pretty soon. And there are two inputs, S and R, set, reason. The outputs are Q and not Q. Q and not Q are always complements, okay? So it's not like my ex-wife, they're always complements. So anyway, and we're going to see how AND gates can actually be used to stroke, or actually it's more correctly called enable. So AND gates can form these enable mechanisms. So now, without further ado, that might be a little big. So you notice, just kind of a little quick rundown. S, SR, standing for set, preset, right? Q, not Q, it's kind of Q, not Q. So these are always going to be complements to each other. Notice that this is a NOR gate, so you have a little bubbles there. And you have this feedback into the other gate, okay? Let's talk about the truth table for this guy. Obviously, 0, 0, 0, 1, 1, 0. And the truth table for this is actually going to be quite a bit different than the things that we've looked at before. So, unlike the other examples, we're not going to start with a person, we're going to start with set equals 1. Okay? So let's start right here. So here's set. Let's say set is 1. Okay? You're right, thank you so much. You're saving this big embarrassment. Now, this is an OR gate, right? Anytime an OR gate has 1, what's the output of the OR gate?
Or NOR, 0.
That's right.
0.
But it's a NOR, so it's 0, right? So if this guy is going to get a 1 in, this has to be a 0, correct? Right? If that has to be a 0, what are we going to feed back here? 0. Okay. Now, so if this is 0, and 0 is feeding back here, and let's see, where's our truth table? 0 reset is 0. So 0 here, 0 here, it's an OR gate. So if it's an OR gate, the output is going to be 0, but it's inverted, correct? So in this case, what's going to be the output? We're good so far? I know it seems like one of these circuitous paths, but grasshopper, you will get it very soon. So what's the state of Q going to be? When we're down here, when set's 1 and reset is 0, what will the state of Q be?
1.
1. What will the state of non-Q be? Yes, I sure can. Sorry. Okay. So not Q is always the opposite of Q, correct? 0. And the mode here, we call that set. So let's get a different color. We're color coordinated today. Now we're going to look at reset. Reset as a 0, reset as a 1. So try to ignore the purple things. Try to ignore the guy behind the curtain. Is that the right markings there? Okay. So input, this is an OR gate, right? So the output right here is going to be a 1. Except that it's inverted, right?
If you move down a bit, I'm sorry.
Right there, perfect.
Is that better?
Perfect.
Yeah.
Right there. Perfect.
Okay, now here we go back in. Reset has a 1 coming in. Since it's an OR gate, out of an OR gate is always going to be 1 if there's a 1 in, right? Except that it's inverted here. So now our output is going to be 0, correct? And that is latching over here. Give me this guy to 0. So 0 and 0 in an OR gate, the output is going to be 0. But since it's inverted, we get a 1. So Q is going to be 0. Not Q is going to be 1. Okay? Now, for a tricky one, 0 and 0. So now I have 0 coming in here, 0 coming in here, blue color. Okay, so 0 in, that's going to be the output of this would, oh gosh, we don't know. Okay. So when we have 0 in, did these change at all? On an OR gate, 0 and whatever else is there is always whatever else is there, correct? So a 0 in for an OR gate won't change that a bit. So in other words, what we're saying is, if we put a 0 in here, and we put a 0 in there, since it's an OR gate, and I know that it's an OR and the opposite is AND, excuse me, the complement. But it's not going to change the output of the OR gate, correct? True or false? True. It's not going to change the output of the OR gate. So we don't really have Q and Q naught. We don't have a 0 or 1 or 1 or 0. We have Q and Q naught. Whatever Q was before, if you set them both equal 0, it's going to be Q. Whatever not Q was before, it's going to be not Q. And so, let's reset here. So this is going to be called no change. So if you set S and R to 0, then the output here flip-flop will change. Okay? With me? Now, it gets really tricky, and I'm running out of pens. So you're going to have to try really hard on these. We're going to put a 1 into both of these. So he comes in here. This is a 1. So what's the output of the OR gate always going to be? It's always going to be 1, correct? But it's inverted, so it inverts to a 0, right? Out here. Same thing here. He has a 1. It inverts to a 0, and now you're going to feed back to a 0. Okay, so what's actually Q and Q going to be? This is a trick question. Is there any way you can truly determine what Q and Q naught are going to be? The answer is no. They're going to be undetermined, and the flip-flop is unable is unable to determine correctly the output states of Q and not. Okay? So we say that when S and R are both 1, we say that the output is not determined. Okay? With me? Now, how did I keep this whole thing? It's not an IQ test. Okay. So this is also an SR flip-flop, right? Set reset flip-flop. Except instead of being made of NOR gates, it's made out of these inverted NAND gates, okay? Let's go through the logic truth table here. 0, 0, 0, 1, 0, 1, 1. Okay, let's do the set reset. Yes, sir.
I do not.
Sure, go ahead. Yeah, have fun.
You don't have one next door.
Okay, let's go when S is 1. So now we have an input of 1 and an input of 0. Correct? So we have the inverters. 0, 1. Now we're into a NAND gate. Okay, this 0, as that 0 goes into an AND gate, what did we find out last week? Anytime any of the inputs into an AND, we'll say AND right now, he knows the name, say AND. Anytime one of the inputs to an AND gate is 0, what is the output of an AND gate going to be? 0. And this one's inverted. So on one side it would be 0, and on the other side it's going to be a 1. Okay. Here we have a 1, so far we don't know, but this guy is going to feed back. It's going to feed back a 1 here. So now you have a 1 and a 1, correct? So the output of that AND gate would be
0.
a 1, except it's an AND gate, so it is 0, correct? So we would have a 1 here, otherwise we have a 0 here. Okay. So Q is 1, not Q is 0, correct? Did I do that right? Did I make any mistakes? Did you follow? Okay, so we're good, right? Okay, now we're going to go back. We're going to go to reset. And reset now will be 1. And set will be 0. So now we have the inversion of both of those. Okay. So anytime the input to an AND gate is 0, the AND gate is 0. So this is 0, but since it's an AND, the output is actually going to be the 1. So far, so good? But that's a 1, and that gets fed back here. Correct? So this is a 1. Here we have a 1 coming in from the signal. So the output is going to be a 1, except it's inverted, so the output is 0. So my truth table for this, to finish up this truth table, is going to be 0, 1. Let's reset and then set. So far, so good? Okay. Without going through it, what? Yes?
How do you know whether you're starting with set or reset? Like you.
Oh, good question. Yeah, I arbitrarily just picked set to start with. But your application, whatever your application happens to be doing, and as you see, some of the examples we're going to do after a while, it's actually undetermined because we don't know what came before. But here, we could have done it either way. We're going to start with you.
Okay, so it matters on what outcome you had previously?
Only for 0, 0. Okay? 0, 0 is the only one that remembers what you have. and so the output is going to remain unchanged. So the same thing happens here. 0, 0 is going to remain unchanged. And so here, I can't write 0 or 1 or 1 or 0. I write Q or not Q, because it's just going to depend on what the state of those were before. So here we're going to say unchanged. And the same thing for 1 and 1. Not the same thing, it's not unchanged. It's undefined. Remember how in algebra when you would say y divided by 0? Start with saying y by 0 is undefined. Remember that? Okay. This is a while back now.
They're undefined and undetermined.
I really should say undetermined, but they're really not. In this case. Let me see if I have my slides here. Okay, so now we have the ability to be a little more precise. And this is similar to what we've already done, except the inputs are reversed instead of the output, right? Okay. And the reason that's important because the feedback doesn't work. Okay, so this is still an SR flip-flop, but it's gated. And this is called the enable channel, okay? And enable has the ability to either let the flip-flop go and be whatever state you want it to be, or inhibit it so it's not going to change regardless. And here's why. So we have two AND gates going, right? So two AND gates. So let's consider this. If this input is 1, now we kind of go back to your identities, right? Anytime you AND with 1, what do you get? You get whatever value it is, whether it's X or 1, right? So based on your identities, we can say that when this is set to 1, whatever you set this to, whatever this becomes, this output will be the same thing. Same thing over here. Let's do a truth table. So, let's see, how many inputs do I have here? 4. I'm going to do it for these two things here. Should have 8, right? X, W, X, Y. Crap. Okay, we'll just draw this and see if I can get this to work. Okay. So I'm running out of paper here. Ah! Let's do a little bit. This is what happens when you use ad hoc things. Let's start off by saying this guy is 0, or disable, not enable, disable, or inhibit. Okay? If this guy is 0, and this guy is 0, the outputs are obviously 0 and 0, correct? What if this guy is 0 and this guy is 1? What are the outputs? 0? What if this guy is 1 and 0 for the outputs? Right, Rick, you're beating a dead horse here. So no matter what you put in to those two inputs, the outputs are always 0, correct? Okay. Let's try to keep this. Now that's a 1. Okay. So if I put a 0 and a 0, obviously the outputs are 0, correct? What about a 0, 1? What are my outputs? 0, 1, right? What about a 1, 0? What are my outputs? 1, 1, 1. So what's the rule we're coming out with on this, this negative flip-flop? How do we summarize what we're seeing here? So the inhibitor is 1. It's just a straight pass-through, right? But when an inhibitor is at 0, nothing gets through, okay? And in this way, it's a lot easier to govern what happens in the flip-flop. Okay, now we have a timing factor. And for these SR flip-flops, that's not too important, but eventually we get to flip-flops that have a clock as an input, okay? So let's go ahead and figure out what our state is. And we don't have not Q, but Q is enough. If we know what Q is, then we know what not Q is, right? Okay, so we start off here. Here we have S is low, and R set is low, reset is high. So what should Q be? Remember your truth table? If reset is a 1, Q should be 0, correct? Who said it? You have it right. So Q is low. Now, right here, we have a change in state. For this number of blocks, we have a change in state. We have low and low. What do we say low and low meant? No change, right? Did we say that? Didn't the truth table say no change? So no change here. Now, set goes high, reset stays low. So what is the value of Q going to be? It's going to be set high. All the way, nothing changes until see, so you with me so far? Now, S goes back down to 0, and R is always. So what happens at that point? What will Q change?
No change.
No change. Excellent. Pay attention. Okay. Now reset changes to 1, or pi. So then what happens to Q?
Reset.
Reset. We go here until there's another change in state. Then what happens? Now we have 0 and 0.
No change.
No change. Now set goes to 1. No change this entire point. Oh, wait, here's a change, right? But do we need to change the output Q? Finally, what happens? Resets. Okay. So, could you do that on a test?
If we had to do the.
This sheet is on the web course, so you can get this in practice. Okay. So you will probably get this on your test. Okay. So now we have this thing called a T flip-flop. And take a look at the circuit down there. What two things do you notice about that? Or you might notice one. There are more things to notice, but what strikes you first? Where's S and R? so we no longer have an SNR, we just have a D and an enable. So it's a lot simpler circuit. And notice that our truth table is a lot simpler too. Okay. So when D is 0, Q is 0, when D is 1, Q is 1. Except when enable is 0, right? When enable is 1, this is still just a passive. When enable is 0, this doesn't make any difference. Stand on his head, it won't make any difference, right? Okay. So before we get to asynchronous, let's go ahead and do a review here.
Okay.
I'm sorry, what? Yes. Okay, so here we have a gauge flip-flop. This is our enable. S, R, and Q. Okay. And once we have Q, we know what Q, or not Q is. Okay. So we start off with S as high and R as high. So what should our state be from the truth table? So what we're going to do is we're going to put a little box here with them. Does that work good, or we don't really know? Okay. Now reset goes low and set goes high. So now legitimately we have what? We have a 1, right? High. Okay. So really, if all you're considering is S and R, for this second block, should it be a 0 or 1? Correct. Except this guy is going to prevent that from passing through. Okay? So we still have an undetermined result. Okay. Now here we have the enable gets set, right? So here we can legitimately say what is the truth table between S and R? And you know, you've already told me the answer, right? It should be 1. That's right. Any change for the next block? No. Any change between S and R right here? Does S and R change there? No. What happens to enable? It gets set to 0. Does that change the output in any way? No. So we keep the same output, no change. Okay. Now enable goes to 1 again, so that means any input changes are going to be reflected in the output, right? But S and R stay the same for 1 more. Now what happens? S goes to 0. R is already at 0, right? So what are we going to change our output to? That's right, nothing. Why? 0, 0 means no change, correct? So we leave alone. Enable goes to 0. But S and R stay the same, it doesn't really matter. When enable goes to 0, we're going to stay the same. Now, you see here when R goes to 1, does that mean our output doesn't change? Why not? Correct. So still no change. Now enable is back up to 1, so that means changes will pass through. So now we're reset, correct? Did I do that right? Yeah. Okay. Okay, now we have Here we have a 0 and a 0, correct? What does 0, 0 mean? Okay. Now we have 0, 0, so we're no longer enabled, correct? No changes whatsoever possible. Right? You guys are going to tell me if I'm making a mistake here. All right, now we're enabled again. But we still have 0, 0 here, correct? So no changes. Enable goes to 0, but these stay at 0 for one more. Now set goes to 1, but are we allowed to make a change? No. Now we're enabled again. Set is at 1, so now are we allowed to make that change? And that goes for what? Goes here, right? Because once enable goes back to 0, there are no changes, correct? Now set goes to 0 here. Does that mean we can make an output change? No. So one more. Now can we make an output change? We could, because enable is set, but there we have 2 zeros, and the truth table tells us that for 2 zeros, no change, right? Okay, now what do we do? We're enabled. Reset goes to 1. Reset, right? And then no more changes. All right? With it? Okay. All this is in the practice sheet. So there's this thing called asynchronous flip-flops, and you have SR and JK asynchronous. And basically these asynchronous chips have like overrides. Okay? Overrides the loss. So take a look. You still have S and R, right? You have enable, Q, and not Q, right? Just like before. But set and reset are overrides. They don't care what enable or S or R are. They're the boss. Okay? So set and reset determine what happens. Except for what is it about set reset? Let's see. See this? The bubble? What does the bubble mean? Inverted, right? So set and reset will only come into play when they're inverted. And you see on the truth table, how many times is set inverted? 0. Once, right? How many times is reset 0? Once. So they're really, in the truth table, they're only a third of the time they're playing a role in the output, right? So you with me? So they're like the override for set reset. Okay. So here we go. Let's see. This first block, are we enabled? We have a 0, so we're not enabled. So how do we know where to start? Any idea? Okay, let's check set and reset. Set and reset. Do they have values that we can actually use for this? Set has a value, right? Now, reset has a 1, but they're inverted, so we don't care if it has 1. We only care if it has a 0, right? Okay, so we can determine the state of this, can't we? Can we determine the state that it starts off? And according to the truth table, what's that going to be? Let's see. Set is a 0. That's where that is, right? Correct? So Q is going to be a 1. Right? Okay, you get that from the truth table. All right, so what comes next? Set goes to a 1 here, so that's not going to come into play. So we you know what would be really good? I have an idea for making this easy. We have to look at set, reset, S and R. So why don't we say, where is it that set and reset have any effect at all on this? There and here. That's the only places they have an effect, correct? Why don't we get get that out of the way now. Then we don't have to worry about it. Okay? So we already did this. How about this next one? Reset is, so we definitely are going to have to set that to 0, correct? Okay. So now we've taken that into account. All right. So now we can count on every 2 blocks being enabled and every two blocks being disabled. This is still a 0. So can we experience any changes whatsoever? I mean, now that set and reset are out of the picture, we can't, right? Now we're enabled. How about S and R? Let's look at S and R. What are they? S is set, R is unset, right? So what is our, according to our truth table, S is 1, R is 0, right? So Q should be 1, right? Okay. No change here. Now enable goes to 0. That's not going to change the state. In fact, that's going to prevent us from changing the state. So far, so good? Now we get enabled again. Any changes yet? Can we make a change here? No? All right, now set S goes down to 0, R is down to 0. What does that signify? Are we allowed to make a change here? Why? Because it's not enabled. Now reset went up to 0 there, or excuse me, to 1. And we are enabled, so what do we do now with our 0, correct? Now we have S and R both at 0, correct? What's that going to mean? We change to here. S goes up to 1. Are we allowed to change it? Now, even though S went up to 1 here, and it is enabled, our reset overrides that, correct? Remember, we set set and reset, we're going to override that regardless. Okay, now we're done with that. Let's see, we're not, right here we're not enabled, so we still have no change. What about the next block? Let's see. R is 0, S is 1, so we go up a notch, right? We go up to 1, is that right? We keep that for 2 at least. Can we keep going at 1? Okay. Now, S goes down to 0. Are we allowed to make a change at that point? We're not enabled, are we? So we can't make a change. But now can we make a change? S is 0 and R is 0. What does that mean? No change. Now R goes to 1. We are enabled, so that means we can't make a change. That's the way that's the end. The opera ends and the curtain goes down. Okay. You guys hanging with me? Got something for me? Okay. So what do we say about the D flip-flop? There's really only one input, correct? Okay. So we have D, Q. All right. So do we know where we're starting? What's our starting value? Can you tell? It's not enabled, is it? I mean, you have something. You have a 1 or a 0, but do you know what it is? don't know what it is. So we're gonna do a little blocky thing here. We're gonna cross hatch. So all we're saying there is we don't know. Okay, now we're enabled, and D is 1. And according to our truth table, what's that give us for Q? Now D goes down to 0. We're still enabled. And we keep our value until where? How long do we keep this guy for? Do we stop there? You sure? Because we're enabled here, so the change should take place right here, correct? But now are we allowed to make a change there? No. Drop down here, correct? Going over here, are we allowed to make a change there? No. I hope they don't do another power tool check here. Did I do that right? No, I didn't. I gotta go down here, correct? I was in HPA 1 a couple, maybe a week ago, and they did a whole power test. Whole power went out. My whole computer went out. It was in the middle of class. Nobody told me. Okay. So now, there's another kind of clock we need to talk about. Talked about it the other day. So this is the type of clock that is only going to fire on leading edge. So the clock will only have an effect here, here, and that's the only time anything can change is on the leading edge of the clock. Okay. So when the clock, at the leading edge of the clock, we're allowed to make a change. Okay? So that's the effect of this clock. You see how it has a little arrow up this way? Okay, so let's go through this. No, first I have an AC and type flip-flop. Let's do that first. It's the last one. Okay, asynchronous D-type flip-flop. See that okay? Same thing, we still have the same tempo. Okay, so do we know what state we're starting with? Do we have any idea what the state is? Let's see. We don't, because the clock is not going to allow us to make a change. Okay? See here, the clock is low, and until we get to the leading edge, we're not going to make it. It's like the enable, except it's a clock that enables us every time we get to that leading edge. Okay? So here we don't know what the output state is. It's something, but we just don't know what it is. Okay? All right. So, how are we going to block out the unknown values? Where's the first place you can possibly figure out the values? There. It's just going to cross-hatch this. We don't know. Okay. Oh, so it's this. So that's the same as set and reset, which overrides it. Okay. So really, if this is an override, and set is 0, and reset is 1, what should the starting value then be? Reset is 0. So, and then S goes up to 1, so then it overrides. See what I'm doing there? So I'm actually made a mistake there. I forgot to take into account set reset.
That reset is the one.
Oh. Okay. So push the speed, how did I gonna mess this? Okay, so reset is 1 here, right? Okay, is that right? When reset is 1, it should go to 0. Right, yeah. Yes, sorry. Okay, so set is 0 here, and that's the only time ever that, so we should have a 1, right? Sorry about all this. So we have set for 2 because the leading edge doesn't fire until there, right? When the leading edge fires, set and reset are out of the picture, correct? Now, what is the state of D? It's 0. So it's going to go to 0. And D stays the same. Now we have to consider what to do here. Are we allowed to change anything here? No change until we get to the leading edge, and we're allowed to make a state change. Okay, we good there? Now D stays the same, so we will keep this all the same. Now we have to decide, are we allowed to make a change? We have to wait till the next one over. No, we have to wait for how long? To the leading edge here, right? We have to make a change there. Now, are we allowed to make a change there? No, because we can only make the change on the leading edge, right? So we'll keep that. Okay. So now we have a JK flip-flop. So let's talk about the truth table for JK flip-flop actually fixes one thing over the set reset. So notice we have JK and a clock, right? So what do you get when they're both ones? What's the state for the mode? Toggle, right? It's no longer undefined or unknown or whatever it turns out to be. It toggles it. While 0, 0 is a no change or a hold, 1, 1 is an automatic toggle. You with me? Okay. Let's go through this. Okay. Do we know? I sure can. Do we know what state we start at? And I'm going to be really careful not to make a mistake. Last one. So we don't have a set reset. And we don't have a leading edge for the first 2, correct? So totally unknown for the first 2, correct? So we'll just cross-hatch this off. I didn't make a mistake, did I? Come to my rescue. I think that's okay. All right, what next? Now we have a leading edge. So we're allowed to change states. So J is a 1 while K is a 0. So what does the truth table tell us for that? Q should be what? 1, right? Is that right? Now we're not going to change here. Now we don't have a leading edge, so we can't change. We can't change until possibly we get here, right? That's our next leading edge. So we have J at 0 and K at 0. What does that mean according to our truth table? No change. So we have to wait until we get to the next leading edge. Okay. Now what? J is 0, K is 1. So Q should be 0. No change until the next leading edge. So now what should we be doing here? There's 0 and 0, and that means no change. Go to the next leading edge. Now j is 1, k is 0, so what does that mean? Go to the next leading edge. No change. Oh no, that is different, isn't it? What do you see here that we haven't really legally seen before? Toggle. And so if we're going to toggle, we're going to do this. Okay. JK. There's one more JK flip-flop. Oh, but what's the difference between this one and the last one? So you have to override, okay? It's a little more complicated, yet these are actually a little more useful in real life. So what's the best thing for us to do here before we go off into la-la land and go from left to right? We should probably factor in a set and reset, right? Isn't that the easiest thing to do? So the only places it does factor in is here and here, right? So what is this going to mean? If reset is 0, what should our state start out at? 0. Good. And here, when set is at 0, our state should be 1, correct? And that's all we have to consider set reset. Okay, now, so where is the next leading edge? Right here? So let's march on over there. Now let's see what that do. What does J and K look like? J is 0. J is 0, so we're not going to make any changes. So we march on over to the next leading edge. Okay. Now what do we have? 1 and 1. So what does that mean? Toggle. Okay. Go to the next leading edge. 0 and 1. What should we do next? K is 1. J is 0 and K is 1. What's the truth table tell us now? Okay. So what do we do there? So this should go to 0, correct? Now what? We go to the next leading edge, except before we get there, we get hijacked, right? Okay. Go to the next leading edge here. So J is 1, 1, so what do we do? Toggle. Let's go to the next leading edge. 1, 0, what should this be? Good. I have one more, just a different JK flip flop. I don't know about you, but this gets old after a while. Does it get old for you? But yeah.
Are you gonna give him the keychain?
And these are online. I'll make sure you have the truth. All you gotta do is trace it through. Yeah. Okay. You don't even need colored pens. It's fine. So, any questions on that? Now, the last thing we're going to do in this section is called Karnoff maps, and that's going to be on Wednesday. And so, anyway, what people do